Hello everyone. So today we are going to discuss about how to analyze a flange beam. So for this we have taken one problem. The problem states like this: determine the ultimate moment of resistance of a beam having a span of 6 meter and a cross section as shown in the figure below. Use Fe250 grade of steel and M20 grade of concrete. Okay, so in the previous class we have discussed about the theory behind uh, a flange beam. We have studied how to find out the depth of neutral axis or different equation for finding out moment of resistance depending upon the depth of neutral axis. And also we have discussed how to find out the flange width if you are talking about a say continuous beam slab system. Okay, so here in this case we have a simple flange which is given here. You can see a simple flange beam. It is not said that it's a continuous, which you can take it as isolated. It's an isolated flange beam, and the width is given as 1000. So we have to check whether it is okay with the flange width that we can find out from IS 456, and the thickness is given as 100 mm, and we have a six numbers of 28 bars which are placed at the web, and the width of the web is 250, and effective depth is 520, and overall depth is 600. So here the thing is, you need to find out what is the moment of resistance, means how much moment it can resist. That is the objective of our problem. So let's go into the problem. So first of all, let's note down our data which are available. The depth of the flange is given as 100 mm. It is as per the drawing. Width of the web 250. Effective depth, that is 520. Area of the steel, which is we have 628 bars. So don't get confused with the availability of bars. 28 bars, whether it's available or not, it uses assume it to be a diameter of bar which is 28 to 628 So the area of 628 bar will be around 3600 square. Then grade of the material, the grade of concrete FCK is given as M20, so 20 MPa, and FY is 250 MPa. Then the span, you can say, the span is given as 6 meters, and which we can assume it to be the L naught that we have discussed in the previous class, which is the distance between the point of zero moment, or you can say the distance between the point of contraflexures. Then actual width of the flange B is given as 1000 mm. This is the actual width, but this is not the width of the flange, because width of the flange should be taken from the IS code. Okay, now let's look into the Codel provisions. I think this provision I have already discussed with you in the previous class. As per clause 23.1.2, we have for a continuous beam slab combinations, we have for T beam, the flange beam equation is given by L naught by 6 plus BW plus 6 DF. For L beam, it is L naught by 12 plus BW plus 3 DF. And if you are talking about some isolated beams, then it is L naught by B plus 4 plus BW. This is for T beam, and if you take the half of what you have got for T beam, then it becomes for the L beam. Okay, so here L naught is basically a distance between the point of zero moments in the beam. So as this is not available in our case, so the L naught, the span which is given in the problem, that we are considering as L naught. So here, as you can see, these two conditions will not be valid for us because this is for continuous, and we have a isolated T beam, so this condition will be valid. So we will be taking this equation to find out the width of the flange. So BF is equal to L naught by B plus 4 plus BW. What is BW? It is the web width, which is 250. L naught is 6000 mm, and B is nothing but the 1000 mm. That means the actual width which is available to you, and it comes out to be 850 mm or 0.85 meter. And here you can see that the width, the flange is basically less than, which is what width you have available with you. Okay, so that is why the BF become 850 mm, that is the width of the flange. But suppose you're in this problem, you got, instead of 0.85 you get 1.2 meter. Here BF is basically more than B, right, where B is 1000 mm or 1 meter. So here, as you can see, BF is basically greater, but what is available is 1 meter. So what is the flange width you have to assume in this case? Here that will be 1000 mm, because this is what actually available to you. So this is, you will be using this is the minimum of these two. Okay, so here the minimum of these two is 0.85 meters, so that is what we are taking as the width of the flange. Then the next thing is to find out the axial limit. As you have understood that the depth of the neutral axis and axial limits are play very crucial role uh, in analyzing as well as designing of flange beam. So let's first find out the axial limit, which is for FE 250 grade, it is 0.53 into D. D is the effective depth is equal to 275.6 mm. Now let's find out what is the actual depth of the neutral axis. Okay, now we have a beam with all the available dimensions as well as steels which are available to us. Everything is given. Now the question is how to find out the moment of resistance. We have different equations. We have basically three equations depending upon the depth of the neutral axis of the stress block. You can say here as if XU is less than DF. This is one equation we had. Then if 3 by 7 XU is more than DF, this is one equation, and 3 by 7 XU is less than DF, right? We had two conditions if you remember in the previous class. Now in our problem we do not know where this exactly the stress block is, or where it actually act, or how it looks like, whether it is whether it say whether the stress block looks like this or it looks like this, we are not sure. Okay, we are not sure, so that is why we are going to assume one by one. Okay, so let us first assume that XU is less than DF. With what does it mean? That means in the flange which is of 100 mm, within this 100 mm your stress block, concrete stress block exists. Okay, so within this portion basically your whole of this is the XU, your whole of the concrete stress block is within the flange. Okay, so this is our first assumption. So this is what we have assumed, that is XU is less than or is equal to DF, and XU is less than is or equal to XU max. Okay, so if this is the condition, I think we have already discussed what is the equation for XU, which is basically same as what we had done for a rectangular beam. Only difference is that B changed to BF, that is the flange width. And if you put the values, AST is the area of steel, we get a value of 131, right? So this is XU is 131.234. But our assumption is, and what is DF? Is this 100 mm? Our assumption is that XU should be less than DF, right? XU should be less than DF, but here you can see XU is greater than DF. So the assumptions that we have made is wrong. It's not correct, right? That means the drawing or the stress block doesn't lie. The concrete stress block doesn't lie within the flange. It lies outside. It lies somewhere like this. Okay, now our second condition comes that this is 3 by 7 XU, whether this 3 by 7 XU is greater than DF or not. This condition, we had the second equation, second case. Here we are assuming that the whole of the flange is having a constant stress which is 0.446 FCK. If you remember, the theory, you will not find it very tough. Okay, so that is why I have already taught you the theory part, so that you do not get any trouble while discussing the problem. So in our case, in the next case, we will consider that XU is greater than DF. Fine. And also 0.43, that means 3 by 7 XU, 3 by 7 XU is basically greater than DF. Okay, or you can say DF by D is less than 0.2. Sorry, it's I think it's greater than 0.2. It is greater than zero point 0.2. Okay, now if this condition is there, then we had the equation for XU, that is the differential axis, as this one: 0.87 FYST minus 0.45 FCK BF minus BW into DF by 0.36 FCK BW. If you understand the theory, I think you can remember this equation. This is nothing but this part or this part are same. From the only this part gets subtracted, and this is nothing but the stress in the, or the force in the concrete block, which is outside of the web. Okay, if we had a flange, something like this, so we are only talking about this part, that part gets subtracted. Okay, so and this comes out to be 146.194 mm. Again, this condition gets satisfied, that is XU is obviously greater than DF. There is okay, but what about the second condition? Let's find out 0.43 of XU. 0.43 of XU becomes 62.863 mm and DF is 100 mm. So our assumption was that 3 by 7 XU should be more than DF, but you can see 3 by 7 or 0.43 XU basically less than DF. So this condition is also not satisfied, so this assumption is also wrong. So then go to the next last assumption, that XU is greater than DF. Fine, but 0.43 XU is less than DF. Here, if you remember, we had a empirical equation to find out the depth of the stress block, or as well as the depth of the you can say the flange portion. This was an empirical equation. In place of, means in all the equations of the previous case, the DF are changed with YF, where YF was 0.15 XU plus 0.65 DF, right? This was what we have done to calculate the YF. So we will be using YF in place of everywhere there is DF. Okay, so now let's see how to solve it. So let's first see that YF is equal to this one. Fine. So in our case, compression force should be equal to the tension force. Now, what is the compression force? So basically for rectangle it is 0.36 FCK BWXU. So plus 0.45 FCK BF minus BW into, in place of there was initially DF, so it was replaced with YF, so YF becomes 0.15 XU plus 0.65 DF into equal to 0.87 FY AST. Okay, this is for nothing but the flange portion except the web. That means the pink portion is for this part and the blue portion is for this part. Okay, this part is for this portion. The compression force over the compression area on the web, in the web area, is given by 0.36 FCK BWXU, and in the flange area it is given by 0.45 FCK BF minus BW, 0.15 XU plus 0.65 DF. Okay, and this should be equal to the tension force, which is 0.87 FYST. Now if you solve it for XU, it comes out to be this one point. You can solve it, I think no need to say it. You can see over here the value of XU that comes out to be 173.237, which basically, if you now find out what is 4 by 3 XU, it is 74 and DF is 100, and our assumption was basically 3 by 7 XU is less than DF. So this condition, the values of XU or 4 by 3, 4 by that is 0.43 XU is comes out to be less than DF, and all the conditions that we have assumed are found to be satisfied, right? So hence the assumptions are correct, and thus the actual value of XU that we can consider for our analysis is 173.237 mm. Okay. Now our objective of the problem is to find out the moment of resistance, that means how much moment it can take. Now we know the depth of XU, so we can now easily find out which equation to be used to find out the moment of resistance. Okay. Now let's see that the calculation of moment of resistance. So let's first find out YF first, because obviously here 3 by 7 XU will be less than DF, so in that case YF should be taken into account. So YF, let's calculate. YF comes out to be 90.986 mm. And if you find out MUR, considering the concrete only, considering concrete only, you will get that the equation is basically the same. This is the force component, this is the lever arm component here, this is the force component, this is the lever arm component over here, and obviously it will give you the moment, and it comes up with 372.598 kilonewton meter. And if you consider the moment of resistance from tension, that means from steel perspective, and assuming that it's in yielding condition, that is 0.87 FIST D minus 0.42 XU, it comes with 359.201 kilonewton meter. You can see that the moment of resistance comparing the steel is basically less than what you can consider for concrete, 372. Okay. So if in the exam it's asked for to find out the moment of resistance, or in general if you are asked to find out the moment of resistance, basically 359.201 is said to be the moment of resistance over here. But the case is, you know that we designed the structures for under reinforced section. That means at the failure, or you can say the steel is going to yield first before letting the concrete to yield. So here it is 372.578, so that means this is the maximum stress in the concrete, or the maximum moment, you can say, considering the stress in the concrete level. Okay. So I hope you have understood this problem and how to find the moment of resistance. We'll go for the designing part in the next class. So with this I would like to conclude today's class. Thank you.